About decoders and encoders. By definition, a decoder is a combinational circuit that has n inputs, whereas the output would be 2 to the power n. For this particular truth table, we have 3 inputs and the output would be 2 to the power 3, or that would be 8 outputs. Now, one thing that is peculiar to this decoder is only one output is high or active at a single time, and this particular truth table also shows that. Okay, only one output would be high at a single time, whereas others would be going to be 0. Now, which output would be high? That depends on the combination of input. Okay, by looking at the truth table, we can deduce that for this first combination, whenever the 3 inputs are low, your D0 output would be high, whereas others would be low. If your input combination is 100, if you consider the second case, your D4 output would be high, whereas the rest of the bits are going to be 0. Okay, so that really depends on the combination input, and the serial number is just like this: 1 2 3 4 0 1 2 3 4 5 6 7 8. And that's why we also name the output accordingly: D of 0, D of 1, D of 2, D of 3. Whenever its respective mean term is activated, like for D0, its respective mean term would be X dash, Y dash, and J dash. If that is there as the input, what happens is D0 goes high, whereas the rest of the bit goes 0. Okay, so that's exactly a decoder is, and we name the decoder accordingly: n by 2 to the power n. For example, for this particular combination, what we have is a 3 by 8 decoder. The input is 3, the output is 8, and we call it 3 by 8 decoder. Okay, now if you're going to implement that decoder, what we do is we take the output as 8, and as I have told you, each output is its respective mean term. So you implement it accordingly, you get the expression accordingly. Now there is no need to add other outputs. Like for this particular function, if you consider these as inputs, these are actually inputs, and this as a function, what will happen is you'll get the function as x dash, y dash, and z dash. Okay, and that's exactly the mean term here is all about. Okay, so you can implement this accordingly. Now the next one would be implementing higher decoder using smaller decoder. Okay, there are multiple times your question comes in the exam like design a higher bit decoder using smaller decoder. For example, if we're going to discuss how we're going to implement a 4 by 16 decoder using multiple 3 by 8 bit decoders. Like in this case, we're going to use smaller decoders like 3 by 8 bit decoders, and we're going to implement a 4 by 16 bit decoder. Okay, now for this, what we have is we have three by 8 bit decoders, and we address it accordingly. Okay, XYZ is there. You have to take the help of truth table here. If you go for like this, XYZ, these are the 3 inputs. Now this is only for 3 by 8 bit decoder. This one is for 3 by 8 decoder. 3 by 8 decoder. There is also another input to the decoder that is known as enable input. Okay, I've written it E here, but that sometime also written as EN. That shows us this is an enable pin. Okay, this shows us this is an enable pin. Whenever that goes high, okay, whenever that goes high, that particular chip is activated, whereas whenever that goes low, that particular chip is deactivated. Okay, that's kind of an enable system. Now if we have two 3 by 8 bit decoders and we have to implement for 4 by 16 bit decoder, what we can do is we can use the first decoder to represent it from D0 to D7, whereas second decoder can be represented second decoder can represent address from D8 to D15 or total of 16 outputs. So what happens in this case is your input should be a 4-bit. As we are designing a decoder, your input should be a 4-bit. Okay, so if you do a truth table of W, X, Y, Z and considering W as the enable, you will see for the first 8 combination this remains 0. For the last 8 combinations it remains 1. So the first 8 combination W remains 0 and this goes 1, this goes 0. So what happens is this chip is activated and depending on these combination your 8 output is activated. Okay, from 0 up to 7. Whenever this particular 8 combination comes into role, your operation switches. This chip is activated whereas this chip is not. And depending on your XYZ value, your D0 up to D15 is activated accordingly. Whereas these D0 up to D7, those are deactivated. So using that, you can implement a D0 up to D15 implementation of this. And thereby you can implement a 4 by 16-bit decoder using a 3 by 8-bit decoder. Okay, smaller decoders. A multiple combination is also possible. Look for the books and you will get multiple examples of this.